2.4 is on the derivative of trigonometric functions. So even though we are not supposed, so this is calculus without early transcendentals, meaning that calculus 1 is not supposed to involve any transcendental functions. These are transcendental functions. So we have trigonometric functions, and they're not supposed to involve, well, e to the x. And it turns out that actually trigonometric functions are just a fancy way of writing exponential functions. So even though we're not supposed to, we will. So let's do section 2.4, derivatives of trigonometric functions. So the first thing I'm going to do here is I'm going to recall Euler's formula. And so it turns out that basically you could have done all of trigonometry in high school, except for those very few things involving right triangles, formulas, which they hardly ever, in high school, I don't think they really even prove any of those. Well, they do have the law of sines and law of cosines. That's about it. And so there are a few formulas. I think in high school, as I said, I think they only give you like 2 of them involving triangles. Other than that, all of the other stuff can all be done in probably an hour, part of a lecture. You can derive everything else by using this formula. So let's derive all of these derivatives using this formula. So let's recall. E to the I theta is equal to cosine theta plus I sine theta. And this is true for any real value theta, so long as we're doing this in radians. So warning, all of these formulas that I will derive involving trigonometric functions only work if we're measuring in radians. If you're not measuring in radians, then everything that I derive is not correct. There'll be some sort of factor that's missing from each of these. And so assume in calculus, always assume, well, in calculus or above, always assume that we are using radian measure unless otherwise specified, because all formulas that you are using will involve radian measure. So now, it turns out that you will show in the, actually in Math 262, that e to the kx, the derivative of e to the kx is just k e to the kx. And so let's, using that fact, which is actually really almost the definition of, it's easily derived from the definition of your exponential function. And so let's look at the derivative of cosine and sine and find and derive their formulas simultaneously using Euler's formula. So the derivative of cosine x plus I times the derivative of sine x is equal to, well, the derivative of the quantity cosine x plus I sine x. But cosine x plus I sine x is just e to the I x. So this is equal to the derivative, e to the I x. Well, to take the derivative, just bring down the constant out in front, I. So this is equal to I times e to the ix. But again, e to the ix is cosine x plus I sine x. So let's multiply I inside the parentheses. So this is equal to I times cosine x plus I squared sine x. But I squared is -1, so minus sine x. But that means that the derivative of cosine x is minus sine x, and the derivative of sine x is cosine x. So we have the following theorems. The derivative of cosine x is minus sine x, and the derivative of sine x is cosine x. Next, let's derive, just because I'm bored, let's derive a whole bunch of formulas of trigonometry in the next minute. So first, let's recall that 1 is equal to e to the 0. But e to the 0 is the same as e to the I theta minus I theta. I thetas cancel. So this is equal to e to the I theta times e to the minus I theta. And so this is equal to e to the I theta times the complex conjugate of e to the I theta. Well, e to the I theta is cosine theta plus I sine theta. The complex conjugate of e to the I theta is cosine theta plus I sine theta. Well, this is the product of the sum and difference two terms. So it's the difference of their squares. So this is equal to cosine squared plus sine squared. And so we have derived Pythagorean's theorem. Cosine squared of theta plus sine squared of theta is equal to 1. Now let's derive the sum and difference formulas for sine and cosine. So cosine alpha plus or minus beta plus I sine alpha plus or minus beta is e to the I times the quantity alpha plus or minus beta. Multiply I inside the parentheses. So this is e to the I theta, e to the I alpha plus or minus I beta. So this is equal to e to the I alpha times e to the plus or minus I beta. And so this is equal to cosine alpha plus I sine alpha times cosine beta plus or minus I sine beta. By the way, from here, we can see that these are equal to this. And so this is equal to, well, let's multiply this out. So cosine times cosine alpha times cosine beta plus or minus I cosine alpha times sine beta. I'm sorry, cosine alpha times sine beta. And let's multiply this. So plus I times I sine alpha times cosine beta. I sine alpha cosine beta. And then I times I is an I squared, which is equal to -1, which makes this plus or minus into a minus or plus, sine alpha, sine beta. Therefore, we have shown that cosine alpha plus beta is cosine alpha times cosine beta minus plus sine alpha sine beta. And so we have that cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. And cosine alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. We also have shown that sine of alpha plus beta is sine alpha cosine beta plus or minus cosine alpha sine beta. sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. And sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. So we've derived, and of course, in the very first step, we derived the Pythagorean theorem. So we derived all of these. All these 5 trigonometric formulas. So that usually takes half of a semester in trigonometry to prove those. And we were able to prove them in less than 5 minutes. Actually, it was 3 minutes. In 3 minutes, we went through half of a trigonometric course, if not more. Actually, that's about 80% of a trigonometric course. Okay, so now we have the following theorem, that the limit as x approaches 0 of the sine of x over x is equal to 1. So let's show that. Let f of x equal sine of x, then f prime of x is equal to cosine x. That was the very first theorem that we did today in this section. So plug in at x equals 0. I have that f prime at 0 is equal to 1. And so 1 is equal to f prime at 0. Well, let's use the difference quotient to rewrite f prime at 0. So this is the limit as h approaches 0 of the sine of 0 plus h minus the sine of 0 all divided by h. Well, 0 plus h is just h. Sine of 0 is 0. So this is the limit as h approaches 0 of the sine of h over h. I'll write this as x's instead of h's. So this is the limit as x approaches 0 of sine x over x, which we have shown is equal to 1. And we are done. In the book, they use a whole bunch of angles to show this. And of course, they also use the sum formulas and different formulas for sine and cosine to show this. But I like this better only because it's shorter. Of course, there's no trigonometry in it, really. It's all algebra. Maybe that's why I like it. There's no trig in this. It's all algebra using Euler's formula. So I guess the nice thing about Euler's formula is that it reduces almost all trigonometry to algebra. Next, limit as x approaches 0, cosine x minus 1 over x is 0. So we're going to do sort of the same thing that we did in the previous proof. Let f of x equal cosine x. Then f prime of x is equal to minus sine x. So f prime of 0 is 0. Sine is 0, 0. So 0 is equal to f prime at 0. Use the difference quotient definition for the derivative. So this is equal to limit as h approaches 0. Cosine 0 plus h minus cosine 0 over h. 0 plus h is h. Cosine of 0 is 1. So this is equal to the limit as h approaches 0 of cosine h minus 1 over h. Let's rewrite each of these h's as an x. So this is equal to the limit as x approaches 0 of cosine x minus 1 over x. And that's what you want to show, that this was equal to 0. Any questions about that? Next, I want to show that the derivative of tangent is secant squared. So we have here. I guess I did it this way. I could have done it where if I would have multiplied, if I would have looked at the derivative of tangent x times cosine x, then I could have derived this also. Then I don't have to use, I wouldn't have to use the quotient rule. I could have just used the product rule. Okay, so the derivative of tangent x is, well, tangent x is sine x over cosine x. Is the derivative of sine x over cosine x. So by the quotient rule, it's the derivative of the numerator, cosine x, times the denominator, cosine x, minus the numerator, sine x, times the derivative of the denominator, derivative of cosine x is minus sine x, all divided by the denominator, cosine x squared. Well, I have cosine squared x, minus and a minus become a plus, sine squared x, but cosine squared x plus sine squared x is 1. 1 over cosine squared of x is 1 over is secant squared of x. And that's what I wanted to show. Let's see. I'm sure it would have been easier if I would have done this. So if I would have just done tangent, done it this way. Derivative of sine x. Well, let's do it this way. So cosine x is the derivative of sine x, and sine tangent x times cosine x is equal to sine x. So let's use the product rule. So it's the derivative of tangent, don't know what that is, times cosine, plus tangent x times the derivative of cosine, which is minus sine x. And so this is tangent x cosine x minus tangent is sine over cosine, so this is sine squared x over cosine x. Add that to both sides of your equation. And so this is equal to so tangent prime of x cosine x is equal to cosine x plus sine squared x over cosine x. Let's get a common denominator. Multiply and divide this by cosine x. So this is equal to cosine squared x over cosine x plus sine squared x over cosine x. But that's just 1 over cosine x, which is secant x. Divide both sides of your equation by cosine. Just the same as multiplying by secant, so you get secant squared. It's not easy. It's longer. Okay, so that's why I didn't do it. Okay, so I thought it would have been shorter, but actually it's slightly longer. Okay, so do it the first way. Any questions about that? That the derivative of tangent is secant squared. Okay. We also have that the derivative of cotangent is negative cosecant squared. So 0 is equal to the derivative of a constant, 1, but tangent x times cotangent x is just equal to 1. So this is the derivative of tangent x times cotangent x. Let's use the product rule. So this is equal to derivative of tangent x times cotangent x plus tangent x times the derivative of cotangent x. We just derived the fact that the derivative of tangent x is secant squared. So this is equal to secant squared x cotangent x plus tangent x times the derivative of cotangent x. So let's bring this to the other side and solve for cotangent, the derivative of cotangent x. So the derivative of cotangent x is equal to minus secant squared x times cotangent x divided by tangent x. But secant squared x is just 1 over cosine squared x. Cotangent x is cosine x over sine x. And tangent x is sine x over cosine x. The cosine squares cancel. So I just get negative 1 over sine squared x, which is a negative cosecant squared x. Okay, so the derivative of cotangent x is negative cosecant x squared because the derivative of 1 is 0, and tangent x times cotangent x is 1. Therefore, the derivative of tangent x times cotangent x is equal to 0. By the product rule, we have that this is equal to derivative of tangent x plus times cotangent x plus tangent x times derivative of cotangent x. Well, we know that the derivative of tangent x is secant squared. Subtract secant squared x times cotangent x from both sides of your equation, and then divide both sides of your equation by tangent x. So I have that the derivative of cotangent x is a negative secant squared x times cotangent x divided by tangent x. Well, let's rewrite secant squared as 1 over cosine squared x. Rewrite cotangent x as, let's see, cosine x over sine x. And let's rewrite tangent x as sine x over cosine x. The cosine x squares cancel. And all that we have remaining is a negative 1 over sine squared x. Well, 1 over sine of x is cosecant x. So this is equal to a negative cosecant squared x. Let's show that the derivative of secant x is secant x times tangent x. Well, 0 is equal to the derivative of 1, which is equal to the derivative of cosine x times secant x. which we can use the product rule on, is equal to the derivative of cosine x times secant x plus cosine x times the derivative of secant x. Well, derivative of cosine x is minus sine x. Secant x is 1 over cosine x. Therefore, sine x times secant x is sine x over cosine x, tangent x. Bring tangent x to the other side of your equation. Divide both sides of your equation by cosine x. Therefore, the derivative of secant x is tangent x over cosine x. Let's write 1 over cosine x is secant x. Therefore, the derivative of secant x is secant x times tangent x. Next, the derivative of secant x is negative cosecant x cotangent x. So 0 is the derivative of 1, which is the derivative of sine x times cosecant x. Use the product rule. So this is equal to cosine x times, well, the derivative of sine x, which is cosine x, times cosecant x plus sine x times the derivative of cosecant x. Let's bring cosine x, cosecant x to the other side of your equation and divide by sine x. Therefore, the derivative of cosecant x is equal to minus cosine x, cosecant x over sine x. Cosine x over sine x is cotangent x. And so this is equal to a negative cosecant x times cotangent x. And that's what you wanted to show. So in summary, let me rewrite what we've shown. So first off, remember that x must be in radians. These formulas do not work if x is not in radians. So you have to make that assumption that x here is in radians. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. The derivative of tangent x is secant squared x. The derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x times tangent x. The derivative of cosecant x is a minus cosecant x cotangent x. So you should be able to see a pattern here that the derivative of the cofunctions, so you have a sine here and a cosine here, is just the negative of the co-function of the derivative. So this is the derivative of sine x is cosine x. So the derivative of cosine x is change it to negative. So it's a negative cosine, so sine. The derivative of tangent x is secant squared. Therefore, the derivative of cotangent x is a minus cosecant squared x. The derivative of secant x is secant x times tangent x. Therefore, the derivative of cosecant x is a negative cosecant times cotangent x. And so you notice this pattern. So really, once you notice this pattern, you really don't have to memorize all 6 of these. Once you know these 3, these other 3 follow. So there's really not 6 things that you have to memorize. You just have to memorize the one fact that to go from here to here, the derivative of the cos. So notice the derivative without any co in front of it are positive. The derivative of the cos are negative, and they're just the co-function of the negative co-function of the derivative of the other one without the co in front of it. Okay. So you really just have to memorize these 3. So I've sort of narrowed it down so you don't have to memorize nearly as many things as you thought you would need to memorize. Next, the limit as x approaches 0 of sine x over x is 1. And the limit as x approaches 0 of cosine x minus 1 over x is 0. Notice that we're doing 0 over 0 and 0 over 0. Oh. So I showed sort of at the very beginning how to find the derivative of sine and cosine just using this easy fact here. Suppose that I don't want to use that fact that the derivative of the exponential function is just the exponential function. So let's reprove this, not using that fact. So the derivative of sine x is cosine x. Well, the derivative of sine x is, well, let's use the difference quotient definition for the derivative. Limit as h approaches 0, sine x plus h minus sine x all divided by h. Let's recall the sum formula for sine. So the sum formula for sine says that sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So now I can simplify this term here using this fact. And so the derivative of sine x is limit as h approaches 0 of, so using this fact, sine x cosine h plus cosine x sine h minus, well, the sine of x all over h. Let me group these 2 terms together. So if I group these 2 terms together, I have, and so let's group these 2 terms together and factor out what's in common, sine x. So this is equal to limit as h approaches 0 of sine of x times the cosine of h minus 1. All plus, well, the second term, cosine x over sine h divided by h. So by the properties of limits, assuming that these limits exist, and we'll show that they do, I'll split this up into 2 pieces. And so the limit as h approaches 0 of this, plus the limit as h approaches 0 of this. Factor out the sine x in front of the limit, since sine of x is constant in terms of h. And so this is equal to sine x times the limit as h approaches 0 of cosine h minus 1 over h plus, well, again, the cosine x is constant. So let's bring it out in front of the limit. So this is cosine x times the limit as h approaches 0 of sine h over h. Well, as h goes to 0, cosine h minus 1 over h goes to 0. As h goes to 0, sine h over h goes to 1. And so sine x times 0 is 0. Cosine x times 1 is cosine x. So this is equal to cosine x. And that's what you wanted to show. So let's do some examples. So on page 150, problems 1 through 16, let me do problem number 4. Y equals 2 secant x minus cosecant x. We will assume without statement that x here is in radians. So unless otherwise stated, you always assume that all measurements are done in radian measure. Okay, so that makes this calculation nice. So this is equal to, oops. So the derivative. Well, I have the sum of two things. So by linearity, this is just equal to 2 times the derivative of secant. Well, the derivative of secant x is secant x tangent x. Minus the derivative of cosecant x. The derivative of cosecant x is a minus, so that minus here becomes plus. Cosecant x, cotangent x. And you're done. Any questions about that? Let me do problem number 16. So first, let me note the following. So we have Leibniz rule, the product rule, which says that the derivative of the product is equal to, well, the derivative of the first times the second plus the first times the derivative of the second. Well, suppose you had 3 functions, f, g, h. Then it's the derivative of the first. And let's write this as g times h, fg, that quantity times h. So this is equal to, and we know that it really doesn't matter how we group things together because, well, the product of functions is associative. So this is just fg prime h plus fg h prime. Well, fg, the product of f and g, again by Leibniz rule, so we're going to use Leibniz rule yet again, is to the first times the second plus the first times the second. Plus this last term, I can get rid of the parentheses. I can multiply h inside the parentheses. So, and of course, this idea will continue if you had more than, 3 terms. So notice the derivative of the product of these 3 terms is the derivative of the first times everything else, plus the derivative of the second times everything else, plus the derivative of the third times everything else. And so you can continue sort of in the same vein, no matter how many terms you have. You just take the derivative of each of them and multiply by everything else, not taking derivatives of those. Okay, so let's take the derivative of y is equal to x squared sine x times tangent x. Okay, so let's take the derivative of this. Derivative of the first, 2x times everything else, plus the derivative of the second times everything else. Derivative of sine is cosine x times everything else, the x squared times tangent x, plus the derivative of the third times everything else. So here's everything else, x squared times sine x, times the derivative of the third, derivative of tangent. The derivative of tangent of x is secant squared x. And you're done. So you take the derivative of the first times everything else, plus derivative of the second times everything else, plus the derivative of the third times everything else. And that gives you your derivative. Any questions about that? Okay. So this is actually kind of a powerful idea. So that means that you can take the derivative of quite complicated functions using that idea. Okay, so there's really only one more idea we have to have for taking derivatives, and then you'll be able to virtually take the derivative of anything. Problem 21 through 24. Find an equation of the tangent line to the curve at the given point. Problem number 24. Y equals x plus tangent x at the point pi, comma pi. So let's first find the slope of the tangent line. To find the slope of the tangent line, I just want to take the derivative. So slope of tangent line. So let's take the derivative. Derivative of x is 1. The derivative of tangent x is secant squared x. And so the slope will equal the derivative evaluated at pi, this pi here. And so this is equal to, 1 plus secant squared pi. Well, cosine of pi is -1. Therefore, secant at pi is -1. -1 squared is 1 plus 1 is 2. Therefore, the slope of my tangent line is 2. I have the point slope form for the equation of a line. Y minus y1 equals mx minus x1. My point is at pi pi, and so the y value is pi. The x value is also pi. And the slope of my tangent line is 2. And that gives me the equation for my tangent line. Any questions about that?
Do you have to simplify the equation further?
Oh, could I? Sure.
Do you have to, if we were they asked that on the exam.
Why would you want to? Why is this not the simplest form?
Would you want us to make it a y equals equation?
You mean make it into the standard form or the general
Correct.
form
Correct.
or the intercept form
Yeah.
or, you know, there are 20 differing forms.
Gotcha.
So which one is the simple form?
We would make it a general form.
Oh, the general form. Okay, so the general form you're saying. So you could just multiply the 2 inside. You could subtract 2x from both sides. Add pi to both sides. So change all the signs. Oh, you want the general form. Oops. Bring pi over to the other side. There. Okay. So if you like that form better, that's fine. But you know, one form is just as good as any other form. So there's really no reason. In other words, there's no reason to do it unless you're specified. And so unless you're specified that you want to put it into a different form, there's really no reason to rewrite it in a different form. Okay. So as I said, only if you happen to be asked that in this case you want to write it in the general form. And so you know, the general form is nice, but you know, okay. It will be actually the general form is nice, especially if you're doing it in multiple dimensions. But you know, in one dimension is not that. No. It's not my favorite form is probably the point slope form. Okay, let me do problems 39 through 50. Find the slope. Find the limit. Sorry. Problems 39 through 50. Find the limit. I keep saying slope. Find the limit. Problem 40. Limit x approaches 0 of sine x divided by the sine of pi x. So first thing to do is to recall the following. That the limit as x approaches 0 of the sine of x over x is equal to 1. So let's somehow try to use that to simplify this. I have the limit here as x approaches 0 and sine x over the sine of pi x. Well, let me rewrite this as something. Well, certainly if I happen to have had x here, then I can use this. Now, of course, oh, maybe actually I should I'll make these into red so you can see what I'm adding. So if this were an x, then I'd be happy because I could use this limit to simplify this. Well, certainly if I divide by x, I had to have multiplied by x. Okay. So then I'm not doing anything. So all I'm doing here is I'm multiplying and dividing by x. So I just change, I'm rewriting 1 in a fancy way. Now, I had here the sine of something over the same thing. Oh, what if I had the sine of this something over the same thing? So what if I wrote this as pi x and pi x? So now I've done nothing here. All I've done is multiply and divided by pi x. And so I've done nothing here or here, except to rewrite things so that'll make my life easier. So first off, what you notice is that the x's cancel. So this is equal to limit as x approaches 0 of the sine of x over x times. Let's take the reciprocal of the second term. Well, that's just sine pi x over pi x. In this last term, the x's cancel, so that's 1 over pi. Well, by the properties in section 1.7, so long as everything exists here, then this is going to equal the limit, so long as these limits exist, and we'll show that they exist in a second. Limit as x approaches 0 of sine x over x times the limit as x goes to 0 of 1 over, actually, let me write it this way, because this is also true, that 1 over the limit as x goes to 0 of the sine of pi x over pi times 1 over pi. I don't need a limit for the pi because, well, it's a constant. So we know that by section 1.7, that is just whatever the limits are times 1 over pi. So this is equal to limit as x goes to 0 of sine of x over x 1 over limit as, well, notice the following. As x goes to 0, pi of x also goes to 0. So I could just say pi x times 1 over pi. Well, as x goes to 0, sine of x over x goes to 1. As pi x goes to 0, the sine of pi x over pi x also goes to 1. So this guy goes to 1, this guy goes to 1, and maybe I'll denote it this way. So this guy here goes to 1. This guy here goes to 1. So I have here 1 times 1 times 1 over pi is 1 over pi. So as x approaches 0 for that quantity here, I get that it's equal to 1 over pi. Any questions about that? Okay. So the idea is just to sort of rearrange it so that you can use what you already know to evaluate your limit. Well, do the same thing. Problem 44. Limit as x approaches 0, sine 3x times sine 5x over x squared. Okay, so let's do this. So this is equal to limit as x approaches 0 of the sine of 3x times the sine of 5x, all divided by x squared. Okay. Now, if I put, and maybe I'll still do it in red, if I put a 3 here, so I'm dividing by 3, but if I divide by 3, I also have to multiply by 3. And if I put a 5 here, so I'm going to have to multiply by 5, then I'm really doing nothing. I'm just multiplying and dividing by the same thing. But as x goes to 0, each of these, just, again, as x goes to 0, 3x goes to 0. Therefore, the sine of 3x over 3x approaches 1. As x goes to 0, 5x goes to 0. Therefore, the sine of 5x over 5x approaches 1 as 5x approaches 0. And well, 15 approaches 15. And so this is equal to 15. Any questions about that? So once you know the trick, then these become quite easy. Okay. Let me do problem number 46. Oh. Limit. Oops. Problem number 46. Limit as x approaches 0. Cosecant x times the sine of x. So let me rewrite this as follows. Well, I have the sine of x. Let me rewrite cosecant x as 1 over sine x. But now, just like before, as x approaches 0, sine of x approaches 0. And so letting sine of x go to 0 is the same as letting x go to 0. And so the sine of x divided by sine x put parentheses here. So I have the limit as blah goes to 0 of the sine of blah divided by blah approaches 1. So the fact that there was a sine of x there didn't really make any difference because, of course, well, it does make a difference because the sine of x goes to 0 as x approaches 0. So since you have that something is going to 0 as your x went to 0, then the sine of that quantity going to 0 divided by that same quantity approaches 1. Due to the fact that the sine of x over x approaches 1 as x goes to 0. So this whole limit here is just equal to 1.